if we live in an expanding universe, that's where the idea of a Big Bang came from. Like that's the Big Bang's idea. There was a competing idea or whatever that came. There have actually been a few of them, like steady state theory, and there's this. It's called plasma cosmology or something like that. I don't know very much about it, but they both failed scientific scrutiny, so we're left with Big Bang.
No. Well, there was like steady state, right? Which definitely is not the case, right? Because, the universe is expanding. Now, the universe expanding came first, Big Bang came second. Because what they thought was, okay, well, if we, play the universe, play the timeline in reverse, then obviously it would lead to Big Bang, right? However,
Right.
much more recent findings by the James Webb Space Telescope gives credence to this idea called, what's it called? Constant expansion. That there was no Big Bang. There was no creation.
You mean eternal inflation?
Yes, exactly.
Eternal inflation works totally fine with a Big Bang.
No, it doesn't, because there is no Big Bang. There's no beginning. So the Big Bang basically says that the universe is only infinite temporally in one direction, not both directions. Right? There's a start to it. Time began at the Big Bang. Now, eternal inflation says it has and always will inflate, and it just would get smaller and smaller and smaller relatively, and there is no beginning and there's actually no Big Bang. And you have this manifold. Oh, I'm sorry, go on.
No, keep going.
And so you have this manifold that exists, and what happens is you have these events where you have matter will spontaneously be created from the latent energy of the quantum vacuum, and over time that iteration will experience heat death, right? And then trillions and trillions and trillions of years later, you'll see, because of probability, right? That's a very low probable event, and you will see that space-time manifold, which is
I got to time you out here for a second.
Yeah, do you think?
You're extremely quiet, and the road noise is pretty loud.
Sorry. I stepped out real quick. And let me know if this is better.
Yeah, it's a lot better.
There we go. Awesome.
So
you have this
eternal inflation just says that multiple Big Bangs produce multiple different observable universes. Eternal inflation and Big Bang absolutely go together. The only difference, or if we even want to call it that, would be Big Bang just applies to our observable universe. It can only tell us about what's going on in this one. Eternal inflation applies to the entire universe. And now I'm hearing myself.
Oh, are you? Hold on. Damn it. Let's see here.
1, 2, 3.
Sorry.
Okay, it's gone. Eternal inflation would apply to like an infinite universe where essentially Big Bangs can happen in different places at different times relative to each other.
Okay. How's that? Sorry.
Sounds fine. Did you hear anything I said?
So I didn't. Beyond the you had said that there's sort of like multiple Big Bang events, right?
Yeah. So there's inflation, and then eternal inflation just basically means that they call them bubble universes, and they happen across the universe in different regions, but they're in non-overlapping observable universes.
So I would also argue that they not necessarily would be completely in a bubble, right? And well, the reason why is this, right? Quantum entanglement. So the way that it works is this, right? Classically, you have these, the universe is expanding, right? And there's an event horizon to our universe, essentially, right? And right, because
there's not an event horizon to the universe. There's an observable, there's an observation limit, but it's not an event horizon.
It most likely is.
No, event horizons are things that black holes have.
So that's true. And it really looks like the universe is a black hole-like object. So if you're
it could be, but the Big Bang could still be true.
Event horizon, we could change the word, right? That's fine. We don't have to call it an event horizon, but there's a boundary, right, that is either expanding away from us faster than the speed of light, or you could just as easily, and the mathematics would show this, we're receding away from it faster than the speed of light. But either way, you have this boundary where no sort of communication and no sort of travel will ever be able to reach it because we can't travel faster than the speed of light, right?
Yeah.
So, right. So now there's two different quantum processes which allow for us to get beyond boundaries such as this. One of them is called quantum tunneling, and the other one is called quantum entanglement.
Quantum tunneling only works at quantum scales. You cannot go beyond the observable universe using quantum tunneling.
Well, so the universe is a quantum object. So
what does that even mean?
The whole thing is quantum scale. The universe is quantum. So there is no
right. That's what I was asking. What does that mean? And you just repeated it.
Yeah. So what I'm saying is that you're saying only on like quantum scales.
Quantum tunneling can only happen across on quantum scales. I cannot. Quantum tunneling is not like large distance teleportation. It's something where a particle can cross a barrier, but on a quantum like scale. It's not like I could go.
So no,
I couldn't.
It just has
The answer is
yes. Yeah, that just has the highest probability of that occurring is over small scales. But there is a non-zero chance that would happen through a larger distance. This is all probability. Quantum physics is all probability. And
I mean,
so
sort of, but it's also like Sean Carroll wrote that paper where he calculated what the odds are that a piano actually could just spontaneously appear in the universe, which it could.
Yep.
And it's the kind of thing where it's like, yeah, it's calculable, but you can also say that it will never happen. You're within reason to do that.
So using that argument, we could also say it's the probability of an entire universe popping into existence, or all the matter of that popping into existence, is so improbable that it probably would never happen, but here we are.
Well, nobody thinks that the universe just popped into existence.
Yeah, we do. That's how it happens. Yes. It comes from the randomness of the quantum vacuum. Yes, that's absolutely
the quantum vacuum is the universe.
Check out.
You should check out Sean Carroll versus William Lane Craig, because William Lane Craig kept trying to make this pops into existence argument, and Sean Carroll spent about an hour telling him that's not what any physicist thinks, and William Lane Craig didn't prepare for anything else other than this unintentional straw man of the position. So he kept saying it for an hour while the physicist kept telling him that's not how it works.
So Leonard Susskind has a different view. And I'm not sure if you're familiar with Leonard Susskind, but check him out. He's not fringe. He's the father of string theory. He's
then he is fringe.
Leading expert on the holographic universe, and also quantum information theory. No, he's very well respected in physics. He is not fringe. He used to be.
If he's a string theorist, he's fringe. because
just that idea is fringe. That's not
yeah,
the only thing that he came up with, right? Not the only thing that he started. That's just one of them. And this recent discovery by the James Webb Space Telescope, where the galaxies are actually have a looks like most of them are rotating in a similar direction, and the leading explanation for that so far is that the universe in and of itself is a black hole type object with angular momentum. Now, with that said, if that is the case, then string theory is much more than likely true.
in addition to autographed copies of both my books and, of course, Spanky, I'm excited to announce that I now have stickers, tumblers, apparel, and more on my store. Take Spanky, the God-defeating penguin, and can you put that into a logical syllogism, with you wherever you go now.
Okay? Google it. Check it out after we're done.
What does this have to do with what we were talking about earlier?
That, so...
Are you trying to tell me that we could use quantumly entangled particles to communicate across beyond the observable universe? Because that's not true. Entanglement doesn't transmit usable information faster than light.
So, it does and it doesn't, but it has to be verified classically. It has to be verified classically, but it does it does allow to for these particles to go through what appears to be wormholes. That's the other thing that Leonard Susskind and I think Juan Maldacena, he'll probably get a Nobel Peace Prize for it, but the famous
probably not peace, but
he's famous for ER equals EPR. He's saying that quantum entanglement and Einstein-Rosen bridges are the same phenomenon.
Eper, huh?
Yeah.
Sounds like a clanker.
Check it out. And so Eper. At any rate, we do have a little bit of a verification of that because they were able to, I think it was Stanford, they were able to teleport and create a traversable wormhole and teleport a tiny bit of information through it using a quantum simulator. So, the other thing, a lot of times when people talk about these things like they're impossible, such as, I remember, so you know who Michio Kaku is?
I know of him, yeah.
I had him as my astronomy teacher at City College in New York City. And, it's funny, we had a little back and forth in class, and he was saying, oh, no, you could never have, because I was like, what happens when electrons fuse? Because I couldn't find any information on that. And he was like, that could never happen because these, the negative forces, the Coulombic forces, would prevent that from ever occurring and for it ever to fuse. And then I was like, well, the same is true for protons. And we know that happens. And he conceded a bit. And do you know how protons actually fuse and overcome that repulsive force?
Are you talking about nuclear fusion?
Yeah, exactly.
Protons don't fuse in nuclear fusion. The number of protons is conserved. No, they don't.
So
you cannot take two protons and fuse them into a heavier hadron or anything like that. That you cannot do that.
The number of protons is conserved, but they are fused because they're not separate.
They're not. I don't know what you think fused means, but to make two nuclei combined together,
touch together.
Yeah, like cosmic docking theory. We talk about it on this channel a lot. But no, you cannot make two protons fuse into one thing. You can make them part of the same nucleus.
Yeah, absolutely. That's what I'm talking about. Yeah, but in theory, that should classical theory that should not be able to happen because they shouldn't be able to touch. I don't think that they become.
But they don't touch. They just become part of the same nucleus.
Yeah, they should not. That should not be able to happen according to classical mechanics. Listen, Google this, right? And the way that it happens, the way that it overcomes the repulsive force, right, is through quantum tunneling. And then, of course, one proton. The universe doesn't like that too much, And so what ends up happening is one of the protons degrades into a neutron, right? And there's like a positron is emitted.
I'm
a
like
high-energy gamma
100%
particle.
sure you're wrong about this, but let's look it up.
No way. Just Google it right now. Yeah. Put in
Quantum
nuclear
tunneling
fusion,
is
quantum
essential
tunneling.
for nuclear fusion. Interesting. I would not have
Damn.
guessed that, because quantum tunneling can happen just on its own with no, like it can happen in a room. So the idea that it would be part of fusion, that seemed really goofy. So I would have guessed that that's not part of
It's
it.
actually one of the reasons why we have DNA mutations, actually, is through quantum tunneling as well.
Well, I'm not
different
going to
topic.
disagree based on my last disagreement. So
Yeah. No, I'm like like a quantum physics nerd. I didn't study it formally, but informally I've been reading about it through scientific literature for like, I don't know, 30 years. I do know my shit to a degree, right? But at any rate, it wouldn't be impossible for that to occur, where you might have entangled particles that, or through quantum tunneling, as unlikely as that might sound.
this is interesting.
It would be possible for that to happen, at least physically possible. Now, you have to keep in mind, if the universe is truly infinite temporally, then what I'm talking about must happen. It might take a trillion to the Google power years.
What has to happen?
You will get a particles to tunnel through those different bubble universes. If it's physically possible, and the universe is, and this is, we're not sure, but we think it is, if it is temporally infinite, then this must occur. If the laws of physics don't expressly forbid it, then that thing would occur in an infinite universe.
Sure, but that doesn't mean that that we would ever have to observe it. It would just have to happen at some point.
That's true.
But that doesn't mean it would.
That's true.
Yeah, that's not a guarantee of getting the chance to.
Yeah, but the other thing is, now hear me out, is a lot of these things are, previously, a lot of these scientific quantum phenomenon, right, were highly improbable to happen, right, until we understood and formalized quantum field theory. And then once we unified, quantum field theory, quantized electromagnetism, etc., we're able to do a whole bunch of different cool shit. Agreed? Like microprocessors,
freaking lasers,
quantum computers, lasers. Yeah. Right? Okay. Now, if we are able to quantize gravity, that would give us some sort of control over space and time, because these things are intimately connected. So, and that's a big if, right? We're not sure if it's quantizable. It looks like it. There's, it's heading towards that direction though. And so we might at some point in our lifetime be able to do this sort of stuff on purpose, to create wormholes purposefully, right? Because it's my opinion. I'm not sure if you're too familiar. Do you know what a white hole is? Get your mind out of the gutter.
No, I wasn't.
No, I know. Okay, that was a bad joke.
I don't think I could come up with the words to describe it.
It's an anti-black hole.
Yeah, it's the opposite. Yeah, it's the opposite of a black hole. But
yeah, it could be possibly, be looked at.
It's like if you pack enough energy into a space, it like goes beyond the wavelength, goes beyond the Planck scale or something.
Yeah, right, exactly. And how could it possibly? So at the point of the singularity, right? At the point of the singularity, time actually ends. That is the point in which time ends in certain respects, in our universe, right? And nothing should pass through it. However, it looks like it might be possible, and of course, good old quantum tunneling. That is how these particles might be able to pass through that singularity and form this anti-black hole or white hole on the other side.
Uh,
So
yeah, I mean, we don't know if white holes exist, though.
we don't, but again, what did we know? If it's not expressly forbidden, right? I'm being a
Well,
little,
that
I'm being,
doesn't
a little, no,
that doesn't work
like
for this.
No, it might, I think it's so, right. If we look at everything else, right, there's, all other phenomenon, all other particles, right? Typically, what we notice is this sort of, second Newton's, second law, right? For every action, there's an equal and opposite reaction. We see all these different particles and antiparticles, right? And so I would argue that if there is this black hole, it's almost certain to have this white hole. But is it certain? Certain, like not really, but it would definitely seem like that's the case. And now, if we look at the history of black holes, we're like, oh my god, no way. It was actually first. They were first thought to have existed black holes in, I think, the 1700s, right? But they were called dark stars, right? And we didn't know, since there was no relativity, they didn't know how it would actually bend space time or whatever. Say again, I'm loud.
Now I'm watching the Broncos and the Eagles just scored.
Okay. Well, hopefully they lose. I'm unfortunately a Giant fan. And they've just been so terrible over the past couple of years. So, but so at any rate, right? These things were theorized to exist, black holes, for hundreds of years, really, right? Because the math of it was simple. If you just had a massive enough object, right, there would be a point at which the escape velocity would be faster than the speed of light. So that that they kind of knew of. And but at any rate, most people didn't believe black holes could possibly be real because of all the different paradoxes and how just fucking weird they are. They thought no way could they possibly exist. And then until we started looking for them, we had the instrumentation to start looking for them. And then what did we do? We discovered them, right? And now it's pretty much in the span of our lifetime went from no fucking way, impossible, this is crazy talk, to they're fucking everywhere. There's probably over 2 trillion galaxies, 2 trillion black holes at the center of each galaxy, right? And then more. Yeah.
Okay, Rebel, I got to interrupt you. Where are we going with this?
My initial thing was that the Big Bang is not true, and it's space and time did not exist at the start of the Big Bang. And the classical Big Bang, that's what they say. Space and time began there. And what I'm saying is,
well, space-time as we understand it, would not have been a thing before the Big Bang.
Exactly. And I'm saying that the manifold of space-time existed before, and it has always existed and is infinite in both directions. And that is the constant expansion, or whatever it's called. And so that's the way I think that makes more sense to me, right? If something was infinite in one direction, I feel almost uncomfortable with that, and I feel more comfortable, although the universe doesn't have to make me feel comfortable, but that it's infinite in both directions. So keep your finger on the pulse with that, and
okay.
just check that out. I don't think actually that there is there was a Big Bang in the classical sense, and space and time did not begin 14 billion years ago, or 13.9.
Well, it only applies to the observable universe, so.
Well, I think so is that the case? I thought no. I thought it did not. It was the entire universe, not just the observable.
I mean, at the very beginning, maybe that's what they thought, but they probably didn't really understand. I don't want to say they didn't understand what the observable universe is. I mean, maybe they did, but because our discoveries just hadn't gone that far yet, nobody back then was realizing, oh, there's an actual visible limit to the universe. But if I were to teleport to the edge of the observable universe, would I not be able to see any farther if I looked that direction? That's not really, I don't see how you could really make that claim. That doesn't seem very reasonable. But anyways, we did 27 minutes. I got to get to some other guests.
One last thing, if you don't mind, going back to the event horizon, right? So, do you know what the Schwarzschild radius is? I'll take about 60 seconds. We'll be done. Do you know what the Schwarzschild radius is?
Yes.
Right? If you do the calculation for the observable universe, the amount of mass, and not dark matter, just the amount of hadronic or fermionic matter, right? Do the calculation for the Schwarzschild radius to see if we're in a black hole or not. I can, cut to the chase. We're within that radius, and it looks, again, that's another piece of evidence that we're actually in a black hole. But check it out for yourself. It's been a pleasure.